session. So today we will study the heap. In our last session we discussed about AVL theory, and today we will discuss all about the heap. So first of all, that we are on binary tree. Heap is also a binary tree, but there's also a kind of a special binary tree. And what is that specialty? That specialty is that first, the heap data structure is a complete binary tree. First of all, it's a complete binary tree, where every node is smaller than its children. Every node is smaller than its children, which is called the min heap. Or sometimes all the nodes are greater than its children, and that is called the max heap. So there are 2 points. First, it is a complete binary tree, and then either that is smaller or greater than. So see in these examples here, complete binary tree, there are many different examples. You can go through all of them and study for your information. But let's see as an example. Let's understand what is a complete binary tree. So I got a brief definition here for that. So a complete binary tree is a binary tree that is completely filled at every level. Every level is filled. Like at every level, all the nodes have 2 children, except possibly the last level. Except the last level. In the last level, all nodes are as far left as possible. It is important that you should remember. Another point, this property allows array representation without gaps. That means when you want to represent an array, represent a tree into an array, you can do that as well. You insert the tree level by level into the array, and that is how you represent a binary tree into an array. It says a binary tree can be stored in an array. You can insert the nodes to the array level by level, leaving out empty if any left child is missing. For example, when you insert this binary tree into an array, so you start from the first level, it is A. So you inserted number A, and then second level BC, then next level DEFG, and then next level HI, and when you come to here you see that one left child is missing, so you leave out that place blank like this, and then you write J. So now, based on this definition, it is not a complete binary tree. It means the some part that a complete binary tree is a tree that completely filled at every level except possibly the last level. So every level is filled, but the last level, if this child was a left child, then this would be a complete binary tree. But right now, it is one left child is missing, and then we have a right. So for that reason, it is not a complete binary tree. Or in another point, when you represent a binary tree into an array, there should not be any blank space. So let's see one more example. It is very small. See this example, for example, first level, second level, third level, and when you come to the fourth level, you see when you start from the left side, every field is filled except this part, which is the right one. That doesn't go against our definition. So that means it is a complete binary tree. Or for example, see this one. This one and this one, they look very similar, but this one is not a complete binary tree, but this one is. How? So let's see. First level, second level, and when you come to the third level, you have the most left node. So that is fine. But here when you come first level, second level, and when you come to the third level, so here some left nodes are missing, then you have the right nodes. And that is how it is not a complete binary tree. So in short, a complete binary tree is filled at every level, or when you represent a binary tree into an array, there should not be blank space. And now you know how to insert nodes into an array. If you are not sure about this, there is a mathematical formula to check the relation between the nodes. That is like this, that every left child is at the location 2i plus 1, and every right child of a node is at the location 2i plus 2. Let's check with this example if this relationship is right or not. For example, consider letter C. So you have inserted everything level by level. Now let's see in the array. You know that in the array index start from 0, so we also started from 0. So 0, 1, 2. So the index of C is 2. Now where is the left child? Where is the F in the array? F is at this position, 2i plus 1. So I is 2, 2 times 2, 4, 4 plus 1, 5. That means F should be the index 5. So let's see, 0, 1, 2, 3, 4, 5. F is there. And see the right child. So the right child is at this place, 2i plus 2. I is 2, 2 times 2, 4, 4 plus 2, 6. So it should be the index 6. 0, 1, 2, 3, 4, 5, 6. So this relation is true with all the nodes if you inserted them to the array correctly. So, and right now you should know at least 3 points. 1, you should be able to represent a binary tree into an array, that you insert the binary tree into an array level by level, and if any node was missing, you always start from the left. If anyone was missing, so you leave a blank space there. And then complete binary tree. So if there was no gap in the array, that means that binary tree is a complete binary tree. You can remember it like that, or you can remember with this definition that all the levels are filled except the last level. Last level also can be filled, but in case it was not filled, but the available nodes should be on the most left side. Okay, so now you know that the heap method structure is a complete binary tree. So now you know that there is a complete binary tree, and there is one more property that you should know, that they are sorted somehow, either from smallest to largest or from largest to smallest. If every node is smaller than its children, it is called mean heap. That means it is sorted from smallest to the largest. Or every node can be greater than its children, which is called max heap. So, and now there is one more point. You should know that why do we use heap in the priority queue? Because in a priority queue, elements with higher priority are dequeued first. And the priority, by higher priority means like sometimes you set a priority from number 1 to larger. For example, number 1 has the higher priority. But sometimes, for example, if you have 100 element, 100 has the higher priority. You define that. You set that rule, that which one of them should be the higher priority. For example, that means you want to design your heap into max heap or min heap. So if it is the max heap, that means the root is the largest one, If it is the mean heap, the root is the smallest one. So for that reason, if it is the mean heap, the root is the smallest one, and when you remove that, so you remove the root or you remove any other node. But as far as you think of a queue, so you start from the one side of the queue, one end of the queue. So for that reason, it is called the priority queue, because the nodes are already sorted based on their value, either in max heap or min heap order. For that reason, we use the heap in the priority queue. So when you study priority queue, you should always remember that there is a tree. So now you should know all how to work with the tree, and then you can use this. And heap sort is the max heap or min heap. So that's all about the heap that you should know. And there are three important operations that you should know with the heap. One is the insertion. It means adding a new node while keeping the max or min heap property. So when you insert a new node in the heap, so if your node is max or min, still you should insert the new node in a place where that property is still stayed the same, max heap or min heap. And deletion, same thing, when you remove a node from the heap. And heapify. So for example, when you have a binary tree, but that is not in order, that is not sorted to max or min heap, so you heapify that. Heapify is the process of converting a binary tree or an array into a heap. Or heapify is the process of creating a heap data structure from a binary tree. It is used to create min heap or max heap. So right now you should know all these definitions, and in the next episode we will start working on these operations: insertion, deletion, and heapify. Until the next lesson, if you have any question, you can add your questions in the comment box. Otherwise, until the next session, have a nice time, everyone.